Have you ever wondered how the universe came into existence? It's a question that has intrigued humans for centuries, sparking profound philosophical debates and driving scientific exploration. And the answer, or at least our best current understanding of it, is quite literally explosive. We're talking about the Big Bang Theory, the reigning champion in the cosmic arena of origin stories. This is not just any theory, mind you. It's a well-substantiated explanation for the birth and evolution of the universe, backed by a wealth of observational evidence. In the early 20th century, scientists proposed a radical idea. Our universe, this mind-bogglingly vast expanse of space filled with galaxies, stars, and all manner of cosmic phenomena, began from an incredibly hot and dense state. Yes, you heard it right. Dense and hot like the core of a star, but unimaginably more so. This initial state didn't hang around for long, though. It expanded rapidly, and I mean really, really fast. This was not your everyday expansion like a balloon filling with air. It was an explosive, accelerating expansion, a cosmic inflation on a scale that's hard to comprehend. And the universe didn't stop there. It evolved, cooled, and continued to expand over billions of years, leading to the formation of galaxies, stars, and planets. From this initial spark, the universe as we know it came into being, with its diverse array of cosmic structures and celestial bodies. Now you might be thinking that's a lot to take in, and you're right. The Big Bang Theory is a profound and complex model, one that offers a glimpse into the very beginning of time and space. It's a model that challenges our understanding, pushing the boundaries of what we know and what we can comprehend. But despite its complexity, the Big Bang Theory presents us with a captivating narrative of cosmic evolution. It provides a framework that helps us make sense of the cosmos and our place within it. So, from a singular point of intense heat and density, we have the sprawling cosmos we see today. How can we be sure about the Big Bang? A pivotal clue comes from the discovery of the cosmic microwave background radiation, or CMB. This fascinating phenomenon was unearthed in 1965 by Arno Penzias and Robert Wilson, and it represents a relic from the universe's infancy. The CMB is residual radiation that was released when the universe transitioned from a hot, opaque state to a cooler, transparent one. This shift happened around 370,000 years after the Big Bang, a moment in cosmic history when atoms could finally form, allowing light to travel freely. The uniformity and isotropy of the CMB across the sky strongly supports the idea of a hot and dense initial state, exactly what the Big Bang Theory proposes. So the CMB, in essence, is a snapshot of the universe when it was just a baby, further solidifying the Big Bang Theory. Did you know that the universe is expanding? This isn't just a wild guess or a random theory. It's a well-established fact backed by substantial evidence. One such piece of evidence comes from a fascinating phenomenon known as redshift. Imagine you're standing by a railway track and a train whizzes past, blowing its horn. As the train approaches, the pitch of the horn sounds higher, but as it moves away, the pitch drops. This change is due to an effect called the Doppler shift. Now let's take this concept to a cosmic level. Light, much like sound, can also experience the Doppler effect. When a galaxy is moving away from us, the light it emits appears to shift towards the longer, redder wavelengths. This is what we call redshift. In the early 20th century, astronomer Edwin Hubble made a groundbreaking discovery. As he observed distant galaxies, he noticed that they were all redshifted. The further away a galaxy was, the more its light was redshifted. This led Hubble to conclude that galaxies are moving away from us. But more importantly, he found that the velocity at which a galaxy is receding is directly proportional to its distance from us. This is the essence of Hubble's law, and it provides a direct link between the redshift of light and the expansion of the universe. Think of the universe like a loaf of raisin bread dough in the oven. As it bakes, the dough expands and the raisins, or galaxies, move farther apart. Hubble's law has profound implications for our understanding of the universe's evolution. It suggests that the universe began from a singular point and has been expanding ever since, a concept central to the Big Bang Theory. So, when you look up at the night sky, remember that those distant specks of light are not static. They're moving away from us. In the grand cosmic dance, galaxies are moving away from us, painting a picture of an expanding universe. What if the universe expanded faster than the speed of light? That's exactly the question that led to the concept of cosmic inflation. Proposed by Alan Guth in the 1980s, this theory suggests a brief period of exponential expansion in the early universe. But why introduce such a radical idea? Well, the Big Bang theory, although incredibly powerful, couldn't explain certain observational puzzles. For instance, why is the universe so homogeneous, with matter distributed so evenly on a large scale? And why does the universe appear to be flat, when the Big Bang theory would predict a curved universe? Enter cosmic inflation. By proposing an intense burst of expansion, it effectively ironed out these wrinkles, making the universe flat and smoothing out any large-scale irregularities. Inflationary cosmology doesn't replace the Big Bang, rather it refines and enhances it. It takes the raw power of the Big Bang and adds a level of precision, offering a more complete picture of our universe's infancy. The notion of cosmic inflation adds a fascinating twist to our understanding of the universe's early moments. Where did all the elements come from? It's a question that takes us back to the very beginnings of our universe, to the moments following the Big Bang. In those first few minutes, the universe was a hot, dense soup of particles, with conditions just right for nuclear fusion. This process, known as nucleosynthesis, began with protons and neutrons colliding to form deuterium, a heavy form of hydrogen. As the universe expanded and cooled, these deuterium nuclei collided with additional protons and neutrons, forming helium and other light elements. Despite the chaos, the process was incredibly efficient, leaving us with a universe filled predominantly with hydrogen and helium and small traces of lithium and beryllium. So, the elements that make up the stars, the planets, and even us have their origins in those critical post-Big Bang minutes. The Big Bang was not just a cosmic explosion, it was also a cosmic forge, creating the building blocks of the universe. What if I told you most of the universe is made up of stuff we can't see or detect directly? Sounds like a science fiction plot, right? But surprisingly, it's the reality of our cosmos. Meet dark matter and dark energy, the universe's most enigmatic characters. Dark matter first entered the cosmic stage when scientists noticed something odd. Galaxies were spinning way too fast. According to the laws of physics, they should tear themselves apart at such speeds. But they don't. Something unseen must be holding them together. That's where dark matter comes in, a mysterious substance inferred from its gravitational effects, believed to constitute about 25% of the universe's mass. But wait, there's more. Enter dark energy, an even more elusive entity. Scientists deduced its existence when they noticed that not only is the universe expanding, but this expansion is accelerating. To explain this, they proposed the existence of dark energy, a strange force that works opposite to gravity, pushing galaxies apart. It's estimated to account for around 70% of the universe's total energy mass. So, between them, dark matter and dark energy make up a whopping 95% of the universe. And yet we know so little about them. They neither emit nor absorb light or any other electromagnetic radiation, making them incredibly difficult to detect. Dark matter and dark energy, these elusive entities, continue to challenge and intrigue scientists. Despite the mysteries, their inferred existence and roles are central to our understanding of the universe's structure and destiny. The universe isn't just a random scattering of galaxies, far from it. It's a complex web of structures, spun together by the threads of gravity. What we see are clusters of galaxies bound together, forming the large-scale structures that make up the cosmic web. These structures, composed of numerous galaxies, are not just fascinating to behold, but they also provide invaluable insights into the distribution of matter in the universe. The formation of these structures can be traced back to the initial conditions set by the Big Bang. Imagine the universe as a soup of matter and energy, bubbling and frothing. As the universe expanded and cooled, minute irregularities in this soup began to grow, pulled together by gravity. Over billions of years, these tiny ripples grew into the vast structures we observe today. The large-scale structures we see are a testament to the initial conditions set by the Big Bang. What's next for the universe, you may wonder? Well, the universe's fate is a cosmic dance between expansion and gravitational attraction. If expansion dominates, we'll witness an ever-spreading cosmos. Yet, if gravity takes the lead, the universe could contract, a possibility often referred to as the Big Crunch. However, the current pace of expansion suggests a ceaseless growth. Whether the universe continues to expand or eventually contracts, its destiny is written in the stars, the galaxies, and the vast cosmic structures we observe today.